Good day, everyone. Welcome to Calculus class. Before we start, let me introduce myself. My name is Daryl Adobas, and I will be your calculus teacher for today. So, for our today's discussion, our topic is induced electromotive forces, also known as EMF, and electric fields. Are you ready, everyone? Please get your notebook and don't forget to copy the important details. So for our introduction, let us define what is induced electromotive forces. Induced electromotive forces, also known as EMFs, is a voltage generated in a conductor when it experiences a change in magnetic flux. It is a fundamental concept in electromagnetic induction discovered by Michael Faraday. Also take note that the law of electromagnetic induction can be interpreted as follows. An electric field is always generated by a changing magnetic flux. Even in free space, where no charges are present, this induced electric field, however, has quite different properties from those of the electrostatic field produced by the stationary charges. Now, who is Michael Faraday? Michael Faraday was an English scientist who contributed to the study of electromagnetism and electrochemistry. His main discoveries include the principles underlying electromagnetic induction, diamagnetism, and electrolysis. Now let us illustrate this. Let's illustrate this point by considering a conducting loop of a radius situated in a uniform magnetic field that is perpendicular to the plane of the loop, as in figure 23.19. As you can see, there is a picture there. That is a figure 23.19 wherein a conducting loop of radius in a uniform magnetic field perpendicular to the plane of the loop. If the magnetic field changes with time, Faraday's law tells us that an EMF represent in this formula. The induced current thus produced implies the presence of an induced electric field that must be tangent to the loop so as to provide an electric forces on the charges around the loop. The work done by the electric field on the loop in moving a test charge Q once around the loop is equal to W is equal to QE, also known as the W. You can call the W work done and equals to QE. The QE represent the force exerted by the electromotive forces. Okay, next. Because the magnitude of the electric force on the charge is QE, the work done on the charge by the electric field can also be expressed from equation 6.8, which is this formula, where 2 pi r is the circumference of the loop. These two expressions for the work must be equal. Therefore, we see that the force exerted by the EMF is equal to force exerted by the EMF times 2 pi r, and it is also equivalent to the second form equation wherein the big letter E, which means magnitude of the EMF or electromotive forces is equivalent to EMF over 2 pi r. Using this 2 pi r means it represents the distance of the charge travels around the loop. Using this result along with Faraday's law and that this formula magnetic flux is equal to BA. The B represent the strength of the magnitude, and A is representing the area of the loop. Is also equals to B pi r raised to 2. For a circular loop, we find that the induced electric field can be expressed in this formula. When you derive it, the final output will be negative R over 2 times dB over dt. Next, the general form of Faraday's law. In general, the magnitude of the EMF for any closed path can be expressed as the integral of electromagnetic force over the path and this formula. Hence, the general form of Faraday's law of induction is this big picture at the bottom. In the middle. Uh, the E represent the line integral equals negative change of the rate of charge of the magnetic flux with the respected time. So when we put it that together, we can read this equation as the line integral of the electric field along with the closed path is equal to the rate of charge of the magnetic flux with the respect of time. Let's have some example. Let's consider a simple example. Imagine we have a coil of wire and we move a magnet towards it. As the magnet gets closer to the magnetic field within the coil chain. I mean, as the magnet gets closer, the magnetic fields within the coil changes. This changes induces an EMF in the coil, creating an electric current. This phenomenon is the basis for many electrical devices, including generators. Next, and that's it. Do you have any questions or clarification? If you have, just comment below. And thank you everyone for listening and have a nice day.